Hello, we are StaRS FInE. I'm Lily.
I'm Whitney.
I'm Sam.
So we're presenting like this because we are the first group today and we spent an hour trying to set up two different projectors. It didn't work, so please bear with us with our presentation on this computer screen.
So StaRS FINE stands for Stacked Rapid Sand Filter Injection and Extraction. Our job is to optimize the way that we extract water from the stacked rapid sand filters that we use in our plants, since the current slotted outlet pipes collect chemical deposits and get clogged very easily. We are one of the last steps in the filtration and plant process and are essential in making sure we can get clean water out of the overall system. We also must be very conscious of major and minor head loss because we have the least amount of head to work with. Based on the past work of other StaRS FINE teams, we are currently optimizing a gravity exclusion method that we will further explain. Figure 1 on this slide is a stacked rapid sand filter apparatus used by the StaRS FINE team in 2015 that is currently taking in water through its inlet pipe below and extracting water from its outlet pipe in the gravity exclusion zones.
So before we had the idea of gravity exclusion, we were using slotted pipes where the outlets would get clogged a lot, and they would get clogged with small particles as well as chemical deposits. And so, unfortunately, the outlet contents in the fall of 2015 looked like those in Figure 5. So we're designing to avoid that.
Alright, so our focus for this project this semester is using a horizontal filtration method to block sand through our outlet pipe while avoiding the slip design at all costs and working with the head loss that's left in the process. To do so, we hope to use a newly designed pine tree pattern for the arrangement of triangular horizontal filters. We hope to have filters inside the tank with an outlet pipe extending outside the tank, which will focus on the sand exclusion zones where water will be more populated. Also, with stacked filters, sand in the region between is facing horizontal filters from the top and the bottom in the stacked triangle, so hopefully that'll increase the optimization of our sand exclusion zones. And we'll begin this task by creating a scaled model to understand more about how this filter will work for us.
So to test the feasibility of our design, we decided it was important to scale it down into something that would fit into a PVC pipe. We worked more with Onshape to curve it and make it 3D printable. And we put it into a PVC pipe with a radius of 4 inches and changed the outlet pipe so we could run it through a peristaltic pump and control the speed of extraction to do tests on failure velocities. The apparatus we created consists of an inlet method, 2 supports for the pine tree structure, and a tube designed to connect to outlet holes for the controlled extraction. The idea for this scaled model was to test by simulating the inside of a stacked rapid sand filter. So ultimately, we can fill this entire apparatus with sand and water and run the test with different filtration and backwash flow rates to find out what velocity sand begins to flow out with water, because that is our failure mode.
So before we finalized the design that we wanted to 3D print, we had to conduct a test that would teach us more about the limits of the pine tree design. So it's important that in our system we have the ability for the sand to be under the influence of gravity so that the particles slide down naturally by themselves. And so if a sand particle were to escape into the water zone for extraction, the particle would fall to the surface of the wing. So if the wing is at least at the angle that we found, which is, as you can see from our data listed, around 26.5, then it'll fall back into the sand exclusion zone, which is what we want. And so therefore, during our test that you can see the setup for in the figure, we measured the minimum inclination that the angle could be to assure that our design was supporting the quality that we need. So based on the design that you can see from Onshape, the model structure of the small sand filter that we tested is what you can see. And so when it came out, it didn't fit into the PVC pipe exactly because it was kind of too exact for the 4-inch diameter. So we needed to sand it down further. And then we carefully placed it in, and it's a very snug fit. And it rests above a smaller PVC pipe, a smaller diameter, that holds it in place. But because there's space between all of the PVC pipes, the water in the sand can flow through freely due to the hollowness of the pipes.
So to match the outlet holes on the filter, in the machine shop, we drilled holes into the PVC pipe that lined up in the location with our 3D printed model. And then, so we did it so that the support could rest above the 2 PVC pipes. And then using 3 small tubes and glue to make the system watertight, we attached pipes to the outlet holes so that water could be extracted, so that it could be attached to a peristaltic pump, which basically extracts water at a controlled rate. And in the test apparatus, which we attached the model inlet pipe to, we attached it to a faucet tap water and the outlet pipe to the extraction pump, as you can see on the right here. Whitney was holding the system, which kind of implicated that we needed something to hold it up if we were going to be running long tests in the future. So we also showed a little support that we built out of wood and a smaller PVC pipe.
So we finally tested this apparatus with just water, and it was successful, which was very exciting. It was almost completely watertight, though there are some bubbles that you can see that indicated like where exactly the issues would be, and we combated this by gluing the lower cap to the PVC tube. We also optimized the extraction rate on the pump so that it would come to a steady state and wouldn't like overflow or like cause anything to happen that would skew our data. The next steps will be to add sand to the system to find different failure rates and to emulate the flow rates of filtration and backwash to simulate the StaRS filters. But we'll have to scale that to the size of the pipe because it will be different from like, the entire stack filter in an actual autoclave plant. And we also have to test the peristaltic pump to make sure that it's actually extracting at the correct speed because it is not perfectly. Yeah. We also designed a stand for more long-term tests.
All right, so thank you for, I'll just talk about this really quick. Thank you for watching our presentation. If you guys have any questions or recommendations, you can feel free to reach out to us. And we have some more information here about some calculations.
So here is just our appendix slide, and what this shows is how we determined the area necessary for the wings of our pine tree design. And so they're accommodating the flow that will be used, where flow is equal to velocity times area. And so in this case, you have to take into account the cross-sectional area of the pipe and multiply that by the velocity of the pipe, and then divide that by the velocity, which is 5 that will be passing through to find the area of the wing, because the area passing through the wing needs to be area times velocity times area times velocity. It's a proportionality. And so all of that information is on this slide, which you can see.
And we use fluidization velocity because that is the speed that we want to avoid the sand following the water out at.
All right.
Thank you.